Hello, everyone. My name is Kwang Sung-ho, and I am an assistant professor at the University of Nebraska, Omaha. Today, I'm going to talk about COCOA, or the Scalable Compute Cost-Aware Data Analytics System. It is an honor for me to give a talk at IC2E 2021. So let me start my talk. Nowadays, many internet applications are running on cloud. For example, Airbnb, Uber, and Netflix utilize the cloud research to serve their users. In this environment, large-scale data is generated and stored in the cloud. For example, user activity log, or system log, or network log. So analyzing such large-scale data is one of the important workloads for these internet applications. This is because they need to make advertisement decision by analyzing user activity log. And then they also need to analyze network log to detect any DOS attack. Or they need to analyze system log to check their cluster health. Because these activities affect their revenue significantly, so complete this data analytic query quickly is one of the important things they have to achieve. Since these data analytic queries may be sent at any time, and then this may incur some peak workload. If they do not have enough computer resource to handle this workload, then they may encounter a performance bottleneck. And the question is how to handle peak workload without performance bottleneck. One of the easiest approach would be deploying redundant virtual machine instances. So by having this redundant computation resource, any queries sent at any time can be processed using these redundant computation resources. However, the problem is a significant additional cost. This is because cloud providers charge for idle resources. So to avoid such significant additional cost, the application may want to make their system scalable. So by making their system scalable, when the query is sent, only small number of minimum number of virtual machine instances can be deployed to handle each queries. So by making their system scalable, they can avoid some extra cost for unused compute resource. However, this because they mainly consider utilizing virtual machine VM, so there is an unavoidable overhead. For example, the VM virtual machine require boot up latencies, which can be up to more than 60 seconds. So if query is latency sensitive, using virtual machine VM is not a good choice. So using serverless will be appealing for this for this application to handle peak workload. This is because serverless provide agility and cost efficiencies and then scalability. So by deploying serverless instead of virtual machines, the data analytic application system can handle peak workload very quickly. So there are many previous work to utilize serverless for data analytic system, to data analytic. However, there are many limitations there for serverless. The serverless only support stateless, and then cloud providers do not allow serverless instances communicate between them, and then serverless only support small, short execution time. Many previous work shows that these limitations can be addressed by using external storage system and some other approach. And then in this work, we also focus more on unit time cost of serverless and then performance of serverless. While these are somewhat mentioned in the previous work, these are not studied well enough for data analytics. So we may mainly focus on these two things of the serverless. So in terms of cost, so while the serverless provide cost efficiencies, it does not mean serverless is cheaper than virtual machines. Because the cloud providers has a heterogeneous pricing policies for their computation resource. Then using serverless may be very expensive. And then this table shows the unit time cost for each cloud providers and then different locations of their data center locations. And then this table shows that serverless can be expensive compared to virtual machines, VM, and then it can be up to 5.8 times. So if data analytics use serverless without consideration of this cost, then they may encounter cost bottleneck. They may pay more than their target project. So in terms of performance, in our preliminary experiment, we found that serverless provide worse performance compared to virtual machines using the same amount of computation resource. So for example, we run the Fibonacci function in EC2 and Lambda, and then we found that virtual machine provide better performance compared to Lambda using same amount of computer resource, dual core, and then 2 gigabyte memory. And then we find the similar result from the using Sysbench, which is popular system benchmark. And then we find that virtual machines provide better performance than Lambda. So this table shows that the comparison between virtual machine and serverless. So in terms of agility, serverless is better because we don't need to wait for the cold boot of virtual machines. And then we can use the computer resource within very small amount of time. However, in terms of performance, virtual machine provide better performance. And then in terms of cost efficiency, serverless provide better cost efficiencies because we applications only need to pay when the code is executed. And then, however, in terms of unit time cost, serverless is very expensive. And then both computation resources have some limitations. So in this work, one of the goals is to get composite benefit from both serverless and virtual machines. So agility and cost efficiencies from serverless, and then performance and cheaper unit time cost from virtual machines. And then we found that if we use these two instances together, we can explore some cost performance and cost performance trade-off space. So, and when is beneficial to use serverless for data analytics? So this figure shows that the expected query execution time, x-axis shows that expected query execution time, and then left y-axis shows the performance improvement and then cost increment when we use serverless over virtual machines. This shows that when we use serverless instead of virtual machines. So if we see if expected query execution time is small, then we can get significant performance improvement by using serverless. This is because of agility of serverless. It means the serverless can be available within very small amount of time, and then the query can be executed very quickly, so we can get the performance benefit. However, this also shows that if query is longer than 120 seconds, we cannot get any performance improvement by using serverless. This is because serverless provide worse performance than virtual machines. And then of course, in terms of cost, using serverless, and then if query is longer, then the application have to pay more extra cost because serverless is very expensive compared to virtual machines. So based on this result, we can consider that if query is short execution time, query has short execution time, serverless can be used to get better performance within a small amount of additional cost. However, each query is longer than 120, then we have to use virtual machine only, because using serverless for long execution query does not yield any performance improvement. And then in this work, we focus on explore these two extremes. And then we consider these two extremes, and then we want to explore this trade-off space. Okay. And then the question is, how can data analytics explore the cost performance trade-off, often by exploring serverless and then virtual machine together? And then to explore this trade-off space, we want to answer the questions. What is the minimum cost to meet target query performance? And then to answer these questions, we built a system called COCOA, which is serverless enabled compute cost aware data analytics system. And then COCOA determines the compute resource configurations, how many serverless instances, and then how many virtual machine instances should be deployed to handle the query without any performance bottleneck while achieving application desired goal. So in this in COCOA, we assume that the system need to deploy some additional compute resource when query set. And then the system can deploy either serverless or virtual machine or both to handle the query. And then if we assume that the virtual machines are deployed, because in virtual machine, in VM, we cannot avoid cold boot up time. So we divide each query execution into two stages. And then in pre-stages means if we consider using virtual machines, we cannot process the query while the VM instances are being deployed. So we call it as a pre-stages. And then after that, in post-stages, virtual machine can process the query. However, if we consider serverless compute resource can process the query from the first when the query is sent. So based on this, our problem model is to determine the numbers of virtual machines and serverless. And then based on this number of instances, we deploy, and then we want to achieve the user applications cost performance goal by deploying this number of virtual machine and serverless. So to get these two number of serverless and the number of virtual machines, the COCOA need to have some input. The first one, to get the user preference, cost performance preference, the user can put the one input threshold. So this is the only input from the application. And then to find the numbers, the input include cloud resource input such as boot up time, and then cost information and so on. And then COCOA also needs some query information, how many tasks, and then how many the stages, and then what is the average, the task execution time, and so on. So the cloud resource informations are rarely changed. So we assume that these inputs are static. However, some input for query is requires some predictions or some requires some information from other system. So in this case, in this work, we assume that these inputs are available from the historical data. And then our future work will determine these numbers precisely by doing some predictions. So based on this input, the COCOA try to solve the first problems to find the minimum total query latencies. So in this case, the COCOA doesn't care about cost, but only focus on what is the best, the minimum query latencies by using many number of instances. So I will not go in detail all of this, but the total query latencies is sum of pre-stage time, and then plus a sum of the pre-stage time and post-stage time. Then once the minimum latencies are determined, computed, then now we need the COCOA determine the target query latencies. So target query latencies can be determined by multiplying minimum latencies and threshold, which is from users. So if threshold is set to 1 by users, that means application want to achieve the best performance, and then they don't want to consider the cost. However, if they want to reduce the cost by enduring some additional latencies, they can increase this value to greater than 1. So we can get the target latencies by multiplying these mean latencies and threshold. So once we get target latencies, then the last problem to COCOA solve is to minimize the query cost. The query cost is a sum of compute cost and storage cost. And then we can get this, try to minimize this overall query cost. And then the last thing the COCOA consider is target latencies as a constraint. So by setting the target latency constraint and then minimize the overall cost, then COCOA allow application explore the trade-off space by setting threshold. So we implement our prototype on Spark, and then we deploy our prototype implementations in AWS, Amazon Web Services, in US East region. Then for the master, Spark master, we use T3X large. And then for the workers, we use T3 small EC2, and then we use Lambda for serverless. And then as you can see, virtual machine and serverlesses both have a dual cores and then 2 GB for each. For the workload, we use TP-CDS, and then we use 3 cores in this work. And then for the low input data, we generated 100 GB TP-CDS raw input and then store in S3 in US East region. To allow the serverless instance communicate each other, we used Redis. So the first experiment what we have done is how we can explore the trade-off space by varying the number of instances. And then this figure shows that when we vary number of virtual machine instances, and then what is the expected query latencies and then cost. And then the right figure shows that when we varying the number of serverless from 5 to 40. And then this both figure clearly show that when we increase the number of instances, we can clearly see the performance improvement. It means the latencies decrease this way. However, the overall cost would be increased. So this one clearly shows that if we deploy more instances, we can get better performance, but overall cost also increased. And then one interesting observation in this result was if we use small number of instances for serverless, it means we may encounter, application may encounter the performance bottleneck because of the lack of computational resource. In this case, the query execution time increased, and then using serverless may not yield any benefit. For example, if number of instances is 5, then we can see serverless provide worse performance than VM, virtual machines. This is because serverless provide poor performance compared to virtual machines. However, the overall cost is inflated because serverless is expensive. However, if we utilize enough resource, then using serverless provide better performance. However, applications have to pay large amount of money compared to virtual machine case. The next experiment was we varied the threshold from 1 to 2. It means if the threshold is set to 1, And application want to achieve the best performance. If they want to set a threshold to 2, it means they want to save the reduce the cost by enduring some additional latencies. So this one clearly shows that when this threshold increased, the overall latencies increased. And then by enduring this increased latencies, application can reduce the overall cost. And then this one clearly shows that the application can explore this trade-off space by adjusting the threshold. So this is all I have for today. And then thank you very much for taking this presentation.